Do you know how to solve this equation? This is a polynomial equation. If you don't, stick around. We're going to talk about exactly how to do that. This is math from the void, where knowledge is power, answers dissolve questions, and where anyone who arrives with an open mind can find their place in the infinite. Let's get started with this. So this is specifically a no calculator problem. This problem would be so easy if you could just throw it into Desmos and see when this graph of a polynomial function, which looks something like that shape, would cross the x-axis. It could possibly cross it once. It could possibly cross it 3 times. We're going to figure out how. So in this video, make sure you have your pen and paper. You won't need graph paper for this one. We're going to solve this using the rational root theorem. Let's align the text a little bit differently. So we're going to use the rational root theorem. You guys might be remembering this if your memory is jogged a little bit with the whole idea of like the P's and Q's. Usually that's a good clue to remind people of how exactly we find these. So the rational root theorem basically says with the P's and Q's, we want to take a ratio P over Q, and we want to consider all such P's and Q's that would make this equation equal to 0 when we plug in the value. So how do we find our P's and Q's? P's are going to be factors of the constant term. So these are going to be your P's. That's going to include plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. We have a lot with this one because 12 is factorable by quite a few different numbers. And our Q's are going to come from this number in front of the leading term. And so our factors are just going to be plus or minus 1, plus or minus 2. So our list of possible rational zeros, there's a theorem, which we're not going to get into. The theorem basically says that if you take any of the P's and divide by any of the Q's, those are possible rational zeros. What does a rational zero mean? We've talked about this before. Rational is just a fancy math word for a fraction. So the ratio here, P over Q, is just a fraction. So all of the numbers that we have to consider is any one of these divided by any one of these. And so let's make our list carefully. If I take any one of these P's and divide it by plus or minus 1, well then of course we just have the list plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And then if we want to divide any of these P's by 2, that's going to give us some more values. So plus or minus 1 over 2. Plus or minus 2 over 2 is just 1, so we don't have to worry about that one again. Plus or minus 3 over 2. Some of these fractions are not going to be as nice to check when we plug them in. Plus or minus 4 over 2, we already have 2, so that's covered. Plus or minus 6 over 2, we already have 3, so that's covered. And plus or minus 12 over 2, we already have 6, so that's covered. So these numbers are possible rational zeros. We don't know if any of them actually are zeros, but here are some great tips for solving this kind of a problem. And this one's not going to be the easiest. It's not going to get solved right away by trying our first guess. Otherwise, that means plus or minus 1 might work. Those are probably the best options to try first. So we're going to basically just calculate a lot of stuff. There's going to be a lot of heavy calculation here. I'm going to put the structure of the equation 2x cubed minus 3x squared. I'm going to place that here. That way we can just kind of plug numbers in and see what's going to work. Lastly, we have minus 12. Now, I'm not going to want a 1. Why do I not want a 1? Well, because minus 17 times 1 is negative 17, and then minus 12, that makes negative 29. There's no way all of this is going to balance out to a positive 29 and give us 0. So that's not going to work to try a few numbers before I give you one of the solutions here, which I just kind of calculated by looking at the options here. I'm sort of doing this in real time, but you can try some of these. Your best options are to try with the easy numbers like plus or minus 1, plus or minus 2, and those will usually find you a 0 along the way. Sometimes if your teacher gives you a tough problem, it might be one of these fractions. So let's plug in one of the fractions just to show you that you don't have to be scared of fractions the way that everyone is scared of fractions. People treat fractions like the boogeyman. Okay, 2 times 1/2 cubed, that's 1/2 times 1/2 times 1/2. So basically that's 1 times 1 times 1 over 2 times 2 times 2, which gives us 1/8. I'll show my work here. And then we have 1/2 times 1/2, which is 1/4. And lastly, we have negative 17 over 2 minus 12. So if we multiply 2 times 1/8, this is like 2 over 1 times 1/8, that's a fourth, minus 3/4 minus 17 over 2 minus 12. Again, these negative values are pretty large, so it's safe to say that that's not going to be giving us a 0. Let's try one last fraction value. Let's try, what can we try? We can try negative 1/2 and see if that changes anything. It's possible that that can change stuff. So let's see. Yeah, it actually doesn't change too much as far as how much I have to write. If I do negative 1/2 cubed, it stays negative 1/8. But then here, when I square it, it stays 1/4. When I multiply negative 17 times negative 1/2, that becomes positive 17 halves. And this is starting to look a little promising. Let's work it out a little bit. So this is negative 1/4 minus 3/4. Sorry, there are construction sounds in the void. It's possible someone is trying to access my escape pod. I'll have to deal with them later. Okay, so we have negative 1/4 and negative 3/4. That gives us negative 4/4 or negative 1. And of course, this is not going to give us 0 because if I'm adding whole numbers with a half, there's just no way that I'm going to get to a 0, right? So all of that to say that trying some of these values won't get you the answer right away. And that is an important lesson in delayed gratification. Just because you're not actually making much progress doesn't mean you should stop trying. You're eliminating possible solutions, which is ultimately getting us to the correct solutions because we have a finite list here. Now, if you want to take a guess on what number is going to work, or if you want to continue, pause the video and continue trying some numbers for yourself, the one that stands out to me is either plus or minus 4, and I think it's going to be a positive 4. So let's try to plug in a 4 and see what happens here. Now, don't use a calculator. Again, this says no calculator. If you have to write things out, I don't care if you have to write things out. I don't care if you have to do 4 times 4 times 4. Then you have to say, okay, that's 16 times 4. And then I don't care if you have to write this out like this, 16 times 4. If you got to do that, I mean, that's what you got to do. Whatever level you're at, make sure to meet yourself honestly at that level. The last thing I want is someone to lie to themselves and be like, oh yeah, I can totally do this by myself. And then they get to a test and they don't know what they're doing. They freeze like a deer in the headlights. So the practice is here. If you're going to make mistakes, do it here in the void where nothing matters. Okay, let's give this a shot. So we have 4 times 4 times 4 is 64. We have 4 squared is 16. And then plugging in a 4 here, 17 times 4 is 68. So let's multiply out. This is 128 minus 48 minus 68 minus 12. And this might seem like it's going to cut it close, but if we subtract these, we get 80. And if we combine these, we get negative 80, which gives us 0. Excellent. We found a solution, and it's a whole number solution, which is kind of nice. But what do we do now? Now that we've found a solution, we're going to use synthetic division. To divide by the newly discovered factor. What is the factor that we discovered? We discovered the factor x minus 4. We use the value x equals 4 because if you notice, if we plug in x equals 4, this is going to give us 0, which is what we were looking for. We were looking for zeros, and we found one of them. So let's use the synthetic division process. I'm not going to teach that to you all over again, but I'm just going to remind you to be careful about it. We put a 4 in the box. We put our coefficients here, so that's to give us a 2, a negative 3, a negative 17, and a negative 12. And what this is going to do, maybe I should include this a little bit, to reduce the original, maybe I'll just underline reduce, the, oops, space, there we go. The original polynomial from a cubic to a quadratic. And so dividing by a factor is going to reduce the power in the polynomial. And so we're going to go from x cubed to something x squared. Let's carry out process of synthetic division. This is going to be an 8. That's going to be a negative 5, which means this is going to be a negative 20. Whoopsie. Negative 3 and 8. I wrote the 8 red, so for some reason that made me think that was like a negative, I guess. So this is 5, and this is going to be positive 20 now. Yes, that's right. This will be a 3, this will be 12, and now our remainder here is 0, which is good, Now these are going to represent the coefficients of the remaining polynomial. So what we're saying here is that the original polynomial is simply x minus 4 times 2x squared plus 5x plus 3. And if you want to check that for yourself, work it all out, and you'll get the original polynomial. You can do it for yourself if you want to check and make sure that you did it correctly. Now, if this is equal to 0, we can find the remaining zeros or solutions because this is a quadratic. We are very familiar with how to solve quadratic equations. We can try to factor it. If we want to, we can just go straight to the quadratic formula, and we won't even have to worry about factoring. But it seems like this factors fairly nicely. Let's try to factor this, yeah? Let's make our x. This is going to be a 6 on top, a 5 here. And that's going to give me 2 and 3, of course. So here we'll have, I use the grouping method personally. You can use any kind of method that you'd like for organizing your results. But I like to use the grouping method. It just encourages you to really be looking at factoring very carefully and understand what you're doing when you factor stuff. So we're going to pull out a 3, and that leaves us with x plus 1. Got us to our first solution. But I just need to see this for myself. And this is something you can do in mathematics when you're really curious. You know, you play around with the numbers a little bit just to be like, wow, did I really miss something? It's possible that I did. Negative 2 minus 3 times 1 plus 17 minus 12. Well, look at that. This one was pretty easy. Maybe I didn't try the positive one and the negative one. Maybe I only tried the positive one. I can't remember. It's lost in the void now. So x equals negative 1 is also a solution here. The numbers were a little nicer than I expected. And what this means here is that we have the x equals negative 1 solution, and as well we have the x equals negative 3/2 solution. So that one would have been the toughest one to find by plugging in values, but all of the solutions here are rational. Now, an important note here, that once we get to a quadratic, factoring doesn't always work out in our favor. Once we arrive at a quadratic, it is possible we will have to use the quadratic formula to solve it, or to find the remaining solutions. So they may not be rational. In this case, it looks like the solutions we found were on that list of rationals, these two. That is not necessarily the case. It's possible we would have had to do some square root business. But nonetheless, here we go. We've solved the equation. Our solutions, I guess I'll just write them here. Our solutions are x equals 4, x equals, negative 1, and x equals negative 3/2. And there we have it. We've done it. So that's a very clear example of how we would use the rational root theorem. Now, if you wanted to graph this as well, I'll just sketch it really quickly. We can use the 0 to help us out, as well as the y-intercept, which is so graciously placed here, negative 12. So that means we would have a spot at negative 12. We would have a 0 at negative 1, and we'd have a 0 at negative 3/2, and we'd have a 0 at x equals 4. So likely does some kind of some kind of business like that. Now, if you're in a calculus class, you will find out exactly where these highest points are located and exactly how high or how low they go. But since we're not in calculus yet, this is just to prepare you for calculus. That's a decent sketch of what it would look like. Okay, let's move on to this problem about functions f and g such that f of g equals g of f, which equals x. Now this is another definition, or another property, I should say, property that describes inverse functions. So whenever you can put one function into another and vice versa and get x, that means you have inverse functions, because functions are like machines. F is like its own machine and g is like its own machine. So if I can take something, let's call it x, and I can put it into the g machine, and then whatever comes out of the g machine, I put that into the f machine, and it brings me back the x that I started with, that means those functions are inverses of each other, because the g function did something to my starting x, but then the f function sort of undid that process, sort of inverted that process, and it left me with the original input. And this needs to work both ways. So if I take my original x and plug it into the f function first, and then take that result and plug it into the g function next, and it undoes the f function, just like the f function undid the g function, then we say they're inverses of each other. So it's saying, what is the relationship between these two functions? They are inverse functions. And I can give you some nice examples. If we take f of x equals e to the x, our inverse function would be the natural logarithm of x. Or if I had some other base, like let's say 4 to the x, then my g of x for the inverse function would be a log base 4 of x. There are other examples with inverses, but I think that covers it for now. So this was a quick trip into the void. We are done for this leg of the journey. This is, I believe it's part 9 of the calc prep. I'll have it properly labeled, but in any event, we will see you next time.